and do the definition of an integral. What's the definition of a derivative, Lucas?
The limit as x approaches delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Delta x can also equal h.
Yeah, you can also have it with h instead. Okay, so that's the derivative of the that's the definition of the derivative. Did I make you solve derivatives at any point this year or last year with the definition? Yes. What's the definition of an integral?
The green sum of I.
You remember? All this thing.
This is the one I
none of us knew. On the triangle.
This is even on the practice AP, and I
got it wrong.
Yes. I didn't even.
Now, it also has to do with the partitions. We actually are going to cover that in a future section, but kiddos, we're going to learn how to solve it with the definition this year. Alright, before we get to that, we need to talk about the fundamentals, and the fundamentals start here. Section 6.1, estimating width, finite sums. Area under the curve. Ooh, what question does it answer? I thought it was just finding the area under the curve. Nope, deeper than that. How instantaneous changes could accumulate over an interval to produce the function that describes the total change. What's interesting about that?
So you measure all the changes to describe the.
And what word did they not use but they meant? Instantaneous changes. What are they talking about?
Rates. Yeah.
So the instantaneous rates, the changes resulting from the rates can accumulate over an interval to produce the function that describes the total change. Interesting. Alright, so the illustration is the one that's down below that you guys should have had ample time to write down. It's a good word. A ship moves along an ocean at a steady rate of 7.5 nautical miles per hour, aka knots, from 7 a.m. to 9 a.m. What is the total distance traveled by the ship?
2 hours.
This is easy. It has a constant rate and it has a time. So therefore,
2
distance
times
equals?
7.5.
2 hours times 7.5.
So yeah, you're going to multiply the 7.5 nautical miles per hour, right? Times 2, and you're going to end up with 15 miles that it's traveled. My question is, why didn't people, when they first taught you the distance equals rate times time, also teach you the idea that you're really just finding an area? What area? If you graph velocity, it's a constant 7.5, and if you measure from 7 to 9, the base is going to be 2, the height is going to be 7.5. We really just found the area of the rectangle, right?
Yeah.
So yes, distance does equal rate times time, but if you graph rate, the area underneath symbolizes that multiplication. Now, how could this get trickier? Yeah, what if your rate varies? True? Which one's more realistic? A constant rate?
No.
No, a varying rate. Okay. Question. How about this one then? How would you guys answer the following?
Okay, the beaches are
Alright, 365.
So the bottom. Oh wait, are you doing it regional sum or integral?
Oh, wait, a year is 1.
Either way.
Integral, because that one's
So it's a constant rate of 3 for all days of 365. Constant. Not even 5. 9. 495. That's not right. 1495. 1095.
Now, what's the way to double check that you're doing it correctly? Dimensional analysis, because you have yards per day times days. Is that going to end up being yards? Whoa, what kind of yards? Cubic yards. Good, talking about the volume. You guys ended up with mental mathers?
1095.
Good.
Those would be yards squared.
Ah, yards cubed.
Oh, yeah.
Because you're not just talking about the surface, you're talking about all the sand, which is a volume. Does that make
Do you want
sense?
to write that as an integral? How would you like?
This would be the same thing as the definite integral from 0 to 365 of 3 D. Could be 3G, 0 to 65. Technically, it's still just distance equals rate times time, but the struggle is we're not really doing distance, now we're doing cubic yards. So we're doing amount equals rate times time. But still find the area, and it was as easy as the time times the rate. So then that brings us up to, okay, but real life, rates are not constant all the time. Actually, they're very rarely constant. And it talks about the motion of people. So, how do you find the area under a curve if we have varying rates or variable rates? Better way of saying it. Yeah. We start with estimation. So our illustration is a particle that starts at x equals 0, moves along the x-axis, so it's just moving horizontally, with the velocity function as is shown. Ooh, the velocity function is now variable, not constant, as shown in the graph below, t squared between 0 and 3. The question is, where is the particle at t equals 3? We know where it starts, so all we need to figure out is the change that occurs. So the question is, how far did it travel in the 3 units? What'd you say, no?
I said what?
You're a genius.
So what do we do?
Integrate from 0 to 3.
Yeah, we need to have the area, right? But if we were to find the area with a triangle, it's going to be a little bit off, so we need integration in order to find that exact area. And just a quick review of, what formula or what idea that I tried to give a special name to because it's so important and shows up so much, talks about how to find the final given the initial and a rate.
The f of the top and f of the
Net
bottom.
change. Integration is net change. What was probably on the AP more than any other topic? Calculus, but then net change. Okay.
What's integration
So,
not change?
good question.
That one formula that's used on like every
Is
single.
it the f of n minus?
Yeah.
Is it the one where we had to like add something extra that everybody kept forgetting to add?
F of A plus N.
To add the initial.
Yeah, that's, yeah.
What is the difference between what they're asking and just if we were justifying the area?
It's not for change. Where is the particle at?
The area just shows the change in. You have to go ahead and add the change in plus where it started from, right? So if I started, and I was measuring away from the podium, if I started negative 10 feet from the podium, if I was negative 10 feet from the podium, right? And you know my rate, and in 2 seconds I end up moving 2 feet. Question, am I 2 feet from the podium? No, you have to take the negative 10 and then you have to subtract 2. You have to know whether the 2 is going to the left or to the right. And then you have to go ahead and add it to the negative 10. Anyway, this would be the notation, but once again, without integration, we know that we would need an area under the curve. True?
Yes, ma'am.
Okay. And we know there's going to be error with area under the curve. Let's keep going. Bridget? Now it gets fun because now they say actually use approximation to solve. So solving a definite integral is not enough. We have to actually use approximations, aka actually use Ringling sums. So kiddos, I already showed you the function. It's t squared plus 1. A traveler shifted up 1. Only between 0 and 5. My question again, do you just care about the change or do you care about the current state of where it is at 5?
Where it is.
Yeah, what they're asking is where it is at 5, true? So it's not just the change, it's actually where it is. Now it says approximate the area under the curve using 5 rectangles of equal widths and heights determined by, equal width and heights determined by the midpoints of the intervals as shown, or as seen. Ignore the example, whatever. Okay, so question, what are my equal widths? Let's review. Riemann sums, how do we do it?
Set a date.
Isn't that 4 with like 5?
Okay, good, so our delta x is gonna end up, or delta t, right?
It'd be 1.
Let's do 1.
Okay. I really want
There's
It
gonna
says
be.
using 5 rectangles.
Yes.
So we have between 5 and 0 cut into fifths, right?
Yeah.
So we can go ahead and use 1. So I'm just showing the width of the rectangles. How are we gonna figure out the heights? That Now, if you guys remember last year, I did this whole like A1, A2, A3, A4, and that was great for illustration purposes. It was just to try to make you remember you have to solve for them separately. But can't we go ahead and maybe list all of those next to each other this year?
Yeah.
Okay. So the area, which is going to, our Riemann sum I should say, which is going to approximate the integral from 0 to 5 of v of t dt. It's going to be found by the following. Base times height, right? Okay. But I have 5 different intervals of bases times height. So I need to go ahead and say, all right, for the first subinterval, my base is going to be 1, because I'm allowed to establish it. But question, what's my height going to be?
We have to use the midpoint.
Uh-huh. And what would be the midpoint of the first subinterval? Y.5?
In between.
So is it my first subinterval between 0 and 1?
Yeah.
Right?
Oh, yeah.
So then halfway between 0 and 1 would be 0.5. I need to plug it into my velocity function.
3/4?
The second area is going to be 1 times, what's my
1.5.
velocity if I'm going now between 1 and 2?
1.5.
You see it?
Yeah. Yeah.
3. That's.
Okay, we get the idea. So long story short, it's going to be all the 1s, bases of 1s, times v of 0.5 plus v of 1.5 plus v of 2.5 plus v of 3.5. When do I stop? I could go on forever. 4.5. Because now I'm done with my interval, right? Now, how can you use your calculator to help this go really fast?
You just plug in the interval above.
No, because you need the approximation. So you plug in this for y equals, and then can't you do y1 of 0.5 plus y1 of 1.5 plus y1 of 2.5 plus y1 of 3.5 plus y1 of 4.5? Yeah. Cool. And then times 1, times 1, done. Question, what are my units?
Does it give you units?
It doesn't, we don't have it.
Units. No.
Struggle, so we can't put any units?
Darn.
It's just units.
It'd probably be some sort of movement. It wouldn't be squared.
Cube.
No,
it would just be.
It would just be units, it would just be miles or feet or meters or yards.
Yeah, let's go.
Okay, now pause. Hold on. This approximates the integral. So what can we say about the position at 5?
Is about.
Below.
Oh.
What do we have to think about the position at 0 plus the area, right? Now, the easy thing with this one, this is why it's kind of lame. What did they make our initial position?
0.
Alright, so that's boring. So 0 plus a, which is going to end up equaling a, you just have to solve it. Right? But, just a quick reminder, integration does not change. If you want to know where you are at, you have to say, where did you start from, plus how did it change? Did anybody plug it in and find it?
Do they?
Well,
They do.
that's okay. We know how to plug it in and find it. Did you find it, Jason?
I did something else, but I
Oh.
don't know if it's gonna work.
Using the Riemann sums with midpoints?
Oh, I put in like the summation thing, and I put
Ooh, that's
y
a
is
great
equal to
idea.
0, and I put n is equal to 4. And for my x value, I put x plus 0.5.
Why would you use a summation?
Because it is a summation.
Because he was trying to do it fast, right? And so if you're trying to do summation, you have to start somewhere, so we could say I is equal to 1, and what'd you go to 5? Is there 5 different subintervals? And then what'd you do?
Well, I
Why'd you
put
do
I is
1?
equal to 0, because
Oh, you went from 0 to 4.
0 to 4, and then for my x value, I put x plus 0.5, parentheses squared plus 1.
Squared?
Yeah.
You're ready to get
Kiddos, here's a quick question before you leave, and then we
Is mine in the grade book?
Hold on. Question. Can summation simplify repeated addition?
Yeah.
Ooh, definition of an integral. Bye guys, see you later. Probably finish this a little bit tomorrow, but you guys can always start.
Yeah. Okay.
Wait, I don't have
One
grade?
that's on the table, Cameron, and then?
Yeah.
Perfect. Grab it if you want it. Bye guys.
Okay, let me just. I'll count through. Please.